Welcome back, everyone. We're diving into some seriously cool science coming out of the 2024 total solar eclipse.
Yeah.
You might think a few minutes of darkness wouldn't be a big deal, right? But
Right.
NASA and a whole bunch of citizen scientists turned it into a massive data gathering event.
Oh, yeah.
We're talking the sun's corona, radio waves bouncing off the atmosphere, and even, get this, student-launched balloons.
It's incredible what we can learn from just a few moments when the moon blocks out the sun's light. It gives us this unique opportunity to study the sun's influence on Earth and even on our technology.
Okay, so let's unpack this, starting with Citizen CATE 2024. Imagine 35 teams spread across the U.S., all poised to capture the sun's corona during totality.
Wow.
But they're not just snapping pretty pictures.
No. It's much more than that. Their goal was to create a detailed time lapse of the corona as the eclipse shadow moved across the continent.
Oh, wow.
And to do this, they used a technique called polarized light imaging. It's like giving our telescopes special sunglasses to filter out specific light waves.
Interesting.
And this helps reveal the sun's magnetic fields and the intricate structures they create in the corona.
So Citizen CATE wasn't just a small group of scientists, right?
Oh, definitely not. It was this amazing collaboration between professional astronomers and dedicated volunteers.
Wow.
They captured over 47,000 images.
47,000.
Yeah, and this data is now being used to create a kind of magnetic map of the sun,
Okay.
which could eventually help us predict things like solar storms.
Oh, right.
Those bursts of energy from the sun that can impact everything from satellites to power grids here on Earth.
Yeah, that's a big deal.
Absolutely.
That's what I call citizen science in action. Speaking of pushing the boundaries, let's talk about NASA's WB-57 jets chasing the eclipse.
Oh, yeah.
Picture this. 2 jets soaring at 50,000 feet, equipped with high-tech cameras and spectrometers,
Right.
all to get an extended look at the eclipse.
The idea was to chase the moon's shadow, giving them over 6 minutes of totality.
6 minutes.
Yeah. Most ground-based observations only get a couple of minutes at most.
Wow. So what did they find? Was it worth the high-flying chase?
Well, there was a slight hiccup.
Oh.
Vibrations from the aircraft blurred some of the images.
Oh, no.
But, they still managed to capture detailed images of the corona.
Okay, good.
And the spectrometers, which are instruments that break down light into different wavelengths, those worked flawlessly.
Wait, back up a sec.
Yeah.
Explain what those wavelengths tell us. It sounds kind of like a sci-fi fingerprint scanner for the sun.
That's a great analogy.
Yeah.
Each element in the sun emits light at specific wavelengths.
Okay.
So by analyzing the spectrum of light, we can figure out the sun's composition and temperature.
So, what did they find? Any interesting elements?
They detected iron in the corona.
Iron.
Yeah. Which is pretty amazing considering it can withstand the intense heat of millions of degrees.
Millions of degrees.
Wow.
So what does this data actually tell us about the sun?
It helps us understand the corona's complex relationship with the solar wind.
Yeah.
That constant stream of charged particles flowing from the sun.
Right.
And this knowledge could one day help us predict and prepare for space weather events that can disrupt our technology and even pose risks to astronauts.
Okay, so we've covered the sun's corona from both the ground and the air. Now let's shift gears and talk about how the eclipse affected us down here on Earth. Did you know that over 6,350 amateur radio operators pitched in as citizen scientists during the eclipse?
That's right.
That's a lot of people tuning in for science.
It really is. The HANA-CI project recruited these ham radio enthusiasts to study how the eclipse affected radio signals and the ionosphere.
The ionosphere.
Yes, it's a layer of Earth atmosphere that's crucial for long-distance communication.
That's a lot of people tuning in for science. What did they find? Was it just static?
Oh, far from it. They collected a whopping 52 million data points.
52 million?
Yeah, and their findings revealed some really surprising things about radio waves. For example, communication at lower frequencies, between 1 and 7 megahertz, actually improved during the eclipse,
Really?
both inside and outside the path of totality.
So the eclipse actually boosted their signals. How does that work?
Well, normally the ionosphere absorbs a lot of those lower frequency radio waves.
Right.
But during the eclipse, the electron density in the ionosphere was reduced, which led to less absorption and clearer signals.
That's incredible. So it's like the eclipse punched a temporary hole in the ionosphere for those radio waves.
You could say that it also had the opposite effect at higher frequencies, 10 megahertz and above.
Okay.
Communication actually got worse. This tells us that the eclipse caused the ionosphere to rise in altitude, which affects how those higher frequency waves bounce around.
So the eclipse created a temporary sweet spot for certain radio frequencies. That's pretty fascinating.
It is. And this information could have practical applications for communication systems, especially during emergencies where reliable radio communication is critical.
Okay, so we've gone from the sun's corona to ham radio waves bouncing off the atmosphere. Now let's talk about something even more visual: student-launched balloons.
I love this project.
The nationwide Eclipse ballooning project had over 800 students sending weather balloons into the path of the eclipse.
It's amazing.
Wow, that's a lot of balloons. What were they hoping to find up there?
Their mission was to study how the eclipse's shadow affected the atmosphere. Think of it like a giant natural experiment. Suddenly, you've got a large area of the Earth's surface cooling and darkening, and that has to have some impact, right?
I imagine. So I'm picturing all sorts of atmospheric weirdness happening. What did they discover?
Well, their findings actually confirm something that scientists had predicted but not directly observed on this scale before.
Gravity waves. Atmospheric gravity waves. Those sound intense. What are they exactly?
Imagine dropping a pebble into a pond. You see those ripples spreading outward.
Yeah.
It's similar in the atmosphere. These waves are disturbances that travel through the air, and they can be triggered by all sorts of things, from thunderstorms to mountains, and in this case, an eclipse.
So the eclipse's shadow created ripples in the atmosphere. How does that even work?
It's all about the tropopause, that boundary layer between the troposphere where our weather happens and the stratosphere above. The eclipse caused a sudden cooling and a shift in air pressure near the tropopause, kind of like a mini sunset effect, and that triggered the gravity waves.
That's wild. So we've got these invisible waves rippling through the air because of the eclipse. Why should we care about that? Do they affect us down here on the ground?
They can actually... These waves transport energy and momentum throughout the atmosphere, and they can influence weather patterns and even affect global circulation.
Wow, that's incredible. And it's thanks to those student scientists and their balloons that we have more data to study this phenomenon. Talk about an impactful science project. You know, it's amazing how all these seemingly separate projects, from capturing images of the corona to tracking radio waves and launching balloons, all tie back to this one event, the 2024 eclipse.
It really highlights the interconnectedness of our world, wouldn't you say?
Yeah.
The sun, the Earth's atmosphere, and even our technology are all linked in ways we're only beginning to understand.
Absolutely. It's like the eclipse gave us a glimpse behind the curtain of the universe, revealing all these hidden connections. Speaking of connections, I'm curious to delve a bit deeper into some of those intriguing findings. Let's go back to Citizen CATE for a moment. You mentioned they're creating a magnetic map of the sun using polarized light. What can those maps tell us about how the sun works, and could they help us predict those solar storms you mentioned earlier?
That's a great question. The sun's magnetic field is incredibly complex and constantly changing. These maps help us visualize the structure and evolution of those magnetic fields, which are the driving force behind solar flares and coronal mass ejections, those bursts of energy and plasma that can disrupt our satellites and power grids.
So it's like having a weather map, but for space weather.
Exactly. By studying these magnetic maps, we can start to identify patterns and precursors that might give us a heads up about impending solar storms. Right now, our ability to predict these events is still limited, but the more data we gather, the better our forecasting will become.
So Citizen CATE isn't just about pretty pictures of the corona. It's about protecting our technology and astronauts from the sun's sometimes unpredictable behavior. That's pretty amazing. Now, those high-flying WB-57 jets also had spectrometers on board to analyze the light from the corona. You mentioned they detected iron at millions of degrees. What does the presence of iron tell us about those extreme temperatures? How can anything survive in that kind of environment?
That's where things get really interesting. Iron at those temperatures isn't like the solid metal we're used to here on Earth. It's actually in a plasma state where the atoms have been stripped of some of their electrons. These highly charged ions emit light at specific wavelengths, which we can then detect with spectrometers.
So by analyzing the light from these iron ions, scientists can figure out the temperature and density of the corona. But how does this information help us understand the solar wind, which you mentioned earlier?
Well, the solar wind originates in the corona. It's this constant stream of charged particles flowing outward from the sun, and it carries the sun's magnetic field out into space. By understanding the conditions in the corona where the solar wind is born, we can get a better handle on its behavior and how it interacts with Earth's magnetic field.
So the data from those jets, even with the blurry pictures, is helping us piece together the puzzle of how the sun influences our planet. I'm starting to see how all these projects connect back to this bigger picture of space weather and its effects on Earth. Now let's loop back to those ham radio operators for a minute. Their findings about how the eclipse affected radio wave propagation were pretty surprising. You said communication at lower frequencies improved while higher frequencies were hampered. What are the practical implications of this for communication systems, especially during emergencies?
That's a really important point. Reliable communication is crucial during emergencies, and understanding how natural events like eclipses can disrupt radio waves is vital for preparedness. The fact that lower frequencies actually benefited from the eclipse suggests we might need to reevaluate our strategies for emergency communication.
So in a way, the eclipse gave us a real-world test case for how our communication systems would hold up under unusual conditions.
Exactly.
Mm-hmm.
And it highlights the importance of considering these kinds of space weather effects when designing resilient communication networks, especially for critical infrastructure and emergency services.
It's a reminder that even something as seemingly benign as an eclipse can have unexpected consequences for our technology. It really underscores how interconnected everything is. Now let's turn our attention back to those student-launched balloons and their atmospheric discoveries. They confirm the existence of these atmospheric gravity waves triggered by the eclipse's shadow. You said they can influence weather patterns. Can you elaborate on that a bit? How do these waves, created by a brief eclipse, have such far-reaching effects?
It's fascinating, really. It's like, the eclipse creates this disturbance in the atmosphere.
Right.
And that disturbance just, propagates outward.
Yeah.
Just like ripples in a pond. And as these waves travel, they interact with the surrounding air, influencing wind patterns, temperature gradients, even cloud formation.
So these waves are like invisible messengers carrying the effects of the eclipse far beyond its immediate path. I'm starting to get a sense of the scale and interconnectedness of it all. We've covered a lot of ground in this deep dive, from the intricacies of the sun's corona to the unexpected behavior of radio waves and the subtle ripples of atmospheric gravity waves. What stands out to you as the most significant takeaway from all of these eclipse discoveries?
For me, it's the reminder that we're still just scratching the surface of understanding our universe.
Right?
We often focus on the big dramatic events, solar flares, volcanic eruptions, hurricanes.
Yeah.
But this eclipse really highlighted the importance of studying the subtle, seemingly transient phenomena as well.
It's like the eclipse gave us a new lens through which to view our world, revealing these hidden connections and processes that are always at play, even when we don't notice them.
Exactly.
Yeah.
And it also underscores the power of collaboration in science.
Oh, yeah.
These discoveries weren't made in isolation. We had professional scientists, amateur astronomers, ham radio operators, and students, all contributing their unique skills and perspectives.
It's a true testament to the power of citizen science and the idea that anyone with curiosity and a bit of ingenuity can make a meaningful contribution to our understanding of the universe. So for all our listeners out there who are feeling inspired, what advice would you give them? Where should they go from here if they want to explore these topics further or even get involved in citizen science projects?
Well, there are so many resources available these days.
Yeah.
NASA has a fantastic website with tons of information on their missions and discoveries, and there are countless citizen science projects out there that welcome volunteers.
That's awesome.
A great starting point would be to look into organizations like the Astronomical Society of the Pacific or the Zooniverse.
Okay.
They offer a wide range of projects for all levels of interest and expertise.
It's amazing to think that someone listening to this right now could make the next big discovery just by following their curiosity and getting involved. What a thought.
Absolutely. And who knows what mysteries the next eclipse will reveal. There's always something new to learn about our universe, and that's what makes science so exciting.
Well said. Thanks for joining us on this deep dive into the world of eclipse science. Until next time, keep looking up and keep exploring.